Hi there. In this video I'll be answering a question on satellites, finding the time taken for a satellite's radio signal to reach Earth and the gravitational field strength it experiences at height above the Earth's surface. This question is from the 2012 Intermediate 2 paper. Sputnik 1, the first man-made satellite, was launched in 1957. It orbited the Earth at a speed of 8,300 metres per second and had a mass of 84 kilograms. We're then told that Sputnik 1 orbited Earth in 100 minutes, and asked to calculate the distance it travelled in this time. Now this is a fairly straightforward question, as long as you remember to convert the time of 100 minutes to seconds. We're using this equation: distance d is equal to speed v multiplied by time t. That's 8,300 multiplied by 100 times 60, which is 49,800,000 metres. Converting this number to scientific notation gives us 4.98 times 10 to the power of 7 metres. Now the next question is a little bit more tricky. A part 2 says, although Sputnik 1 travelled at a constant speed in a circular orbit, it accelerated continuously. Explain this statement. Now to answer this question, we need to know what acceleration actually is. It's the change in velocity of an object in 1 second. Not the change in speed in 1 second, but change in velocity in 1 second. And remember that velocity is a vector quantity, so it has a direction as well as a magnitude or size. The size of Sputnik's velocity, 8,300 metres per second, isn't changing, but as it orbits the Earth, its direction certainly is. So since Sputnik 1's direction is changing, its velocity is also changing, so it must have an acceleration. You'll maybe have to think about this one for a while before it makes perfect sense. This is part B of the question. Sputnik 1 transmitted radio signals a distance of 800 kilometres to the surface of the Earth. Calculate the time taken for the signals to reach the Earth's surface. So we're told the distance, and by the way, remember to convert this to metres, and asked to calculate the time. The only thing we don't know is the speed of the radio waves. This can be found in the datasheet at the front of the exam, as long as you remember that radio waves travel at the same speed as light in air. That's because both radio waves and visible light are members of the electromagnetic spectrum, together with microwaves, infrared, ultraviolet, X-rays and gamma rays. That means that radio waves travel at 3 times 10 to the power of 8 metres per second in air. To calculate time, we use the same equation as before, then rearrange it to make time the subject by dividing both sides by speed v. We then substitute our values into this equation, which, when displayed in the majority of calculators, gives us this. The dot above the 6 means that it's a recurring decimal, so we have a time of 0.002666666666666 and so on seconds. The only problem is that we're not allowed to write recurring decimals in physics, as it indicates an infinite number of decimal places, and we can never measure anything that accurately. So in this case, we round our answer to 0.0027 seconds. Next up, it's part C of the question. The graph shows how gravitational field strength varies with height above the centre of the Earth. Part 1 then asks us to define the term gravitational field strength. Now if you're not sure of your National 5 physics definitions, then take a look at this series of videos I produced, which cover the important terms for all 6 topics. Gravitational field strength is covered in video 1, Dynamics, which says that it's the weight of 1 kilogram. Like many definitions, you can use an equation to help you work this out. This equation tells us that weight in newtons is equal to mass in kilograms times gravitational field strength g. Rearranging to make g the subject, we get gravitational field strength equals weight divided by mass in kilograms. C part 2 asks, what's the value of the gravitational field strength at a height of 800 kilometres? All we have to do here is, with a trusty ruler, get one in your pencil case now, draw a line from 800 kilometres on the x-axis upwards until it hits the line of the graph, then horizontally along to the y-axis. You should then see that gravitational field strength at this height is 7.8 newtons per kilogram. Finally, part 3 asks us to calculate the weight of Sputnik 1 at this height. Now we just worked out the gravitational field strength at a height of 800 kilometres is 7.8 newtons per kilogram. And this is the equation that links weight to gravitational field strength. We saw it earlier in the question. So substituting our values of mass m and gravitational field strength g, we get 84 times 7.8, which is 655.2 newtons, or 660 newtons to two significant figures. If you're not sure where the value for mass came from, we were given it all the way back at the start of the question. Now sadly, that's the end of yet another video. Hopefully you found it useful and been inspired to recommend it to your friends, family, physics teacher, and anyone else who will listen. For more information on upcoming videos, summary sheets and so on, visit physics-podcast.co.uk. Thank you for listening.